There we go. It says the Hangout on air is live. Hey there, welcome everybody to Astronomy Daily Live. Let's see, it's 2 hours UTC on the 10th of January 2019. We're already 10 days into this crazy year. So wow, yeah, pretty amazing. Time seems to be going by at a pretty good clip. So yeah, hope everybody's doing well. So this live stream is for everyone, right? It's for the newbie, it's for the amateur, it's for the pro. I like to talk about all facets of astronomy and space and science and all kinds of other nerdy things. Whatever we sort of like. But primarily the focus is going to be the science of astronomy because that's what my thing is, and this is sort of my virtual porch. So when you come here, be fully prepared to get an earful of science and astronomy, space stuff, and probably all other kinds of nerdy things too. So yeah, welcome. Come on in, everyone. I'm gonna check the chat really quick here, make sure everything's going good. Uncle Bill, nice to see you in the chat. Nice to see you in the chat. Yeah, I mentioned on the Discord yesterday that a year ago, and one can't really help but pay attention to these kinds of things. But a year ago, I was right in the process of sort of announcing that it's going to be a certain number of days before I actually start. I guess I started on UT time January 14th of last year. So today's January 10th. So yeah, just 4 days to a full year doing this, and it definitely feels like it's been a while. It actually feels as though I've been doing this for a lot longer, and that's primarily because except for this, right? Except for me going live and sort of talking out loud, which I'm a really quiet dude, right? I mean, I think I say more words in this hour than I do all day long, right? I mean, I think for sure. But of course, the thoughts are not necessarily racing, but they're going along at a pretty good clip. So I've been doing this kind of thing where my local time here is 7:04 p.m. and for years and years and years, each evening I've sat down and I've looked at astronomical things and I've thought about astronomical things. And so I'm pretty much doing exactly what I've always done for years and years, 20 years, easy. So, doing this like this for, the past year is just a slight different change to that. And it's just to sort of spread the passion around, right? I mean, I don't have a lot to give, but what I do have, I'd like to give it away. And one of the things that I do have an abundance of is a passion for, science and astronomy and all of that. So come on in, welcome everybody. And once again on the panel is Bobby. Hey, Bobby.
Hey, this guy is right here joining the show.
He's right there. I see him.
Ow!
What's going on over there?
Nothing much. We was talking about like how NASA has been affected by the shutdown, and what I do to think about if Nancy Pelosi would just say, okay, if we say that we're gonna open up the if we open up the government now and give you the wall later, would you just do it? Now, if you was Trump, would you just do it? Reopen the government and then later do that wall?
You know, I always, you know, sort of in the back of my mind, I always hope that, you know, if these shutdowns go on long enough, that people will actually realize it's like, huh, you know, maybe we don't need the government as much as we think we do. So, but that never happens, right? You know, because it's a, you know, it's sort of seen as a crisis, and you know that needs to be fixed because surely, you know, we need our government around, you know, to run things. So you know, it never lasts long enough, you know, for people to really start thinking that way. It's sort of like, you know, when the electricity gets shut off, right? Um, you know, right at first it's like, oh no, oh man, this is really bad, right? This is really bad. And then if it goes on, you know, for, you know, an hour or two or so, right around, you know, about hour two, um, of course, knowing that it's probably going to come back on, I can sit back and you know be like, wow, you know, this isn't too bad. And you know, if it wasn't for you the fact that I've got stuff in the fridge, and you know I can't get onto the internet here, this really isn't all that bad. It's not all that bad. And right about then, you know, the electricity comes back on, and it's like, okay, well, all right, back to normal. So
I remember that during my school days, when the electricity goes out, we just play games, and when the lights come back on, back to work.
yeah, 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 and you know, they're, you know, I mean, but you know, what if those lights never came back on, right? You know, what if it went on for days and then weeks and then months and then years, right? I mean, that would sort of be a different story because then, you know, people would actually have to do something, right? It's like, okay, you know, like the electricity isn't coming back, we got to do something about this, right? And that that just in and of itself, you know, would mobilize people quite a bit. And you know, I think the electricity would come back on all by itself. So you know, because you know, people, you know, would be motivated, you know, to do that. So whether that's going to happen, you know, the government kind of thing, nah, it's not. But
You
that's
know,
okay.
if
That's all
let's
right.
just say, like, if it goes like 2 months and stuff, do you think the people will be traveling to the White House and say, "We want what do we want? The government reopen when we want it now"?
Yeah, I don't know. I don't know. Could happen. Could happen. But you know, most people want and sort of appreciate, you know, the government services, rightly so, I suppose. So you know, if that's what people want, that's what they're going to get. So, all right. Well, enough about that. Let's think about the universe for a little while
And
here.
Eddie Conway, the only one that needs the government is the government.
Well, you know, that's an interesting thought. I don't know. I don't know. You know, I mean, you know, there, you know, there may be a place for it. Don't know. Don't know. I mean,
And
we
if it goes,
humans.
let's just say, like, if it goes longer, then we'll just have no choice but to riot and really, like, occupy the White House and stuff, occupy the Capitol or
Yeah,
whatever.
I don't really see any need, you know, for rioting or any kind of violence at all. It's like, well, you know, we have a problem to solve. Let's solve it. You know, let's be intelligent about it.
And our president always says, if you protest peacefully, your voice will be done. Your voice will be good.
Yeah,
But if
yeah.
you go up and have riot and like loot and stuff like that, that's when we got a problem.
Well, yeah, you know, because that's just sort of human nature too. So, all
Right
right,
to
well, cool.
protest, but no right to riot, violence, and all that.
Well, that doesn't really get you anywhere anyway. So, it just, you know, tends to make things a little bit worse. So, all right, well, cool. You know, I past couple of days. Well, I'll give you two updates. First update is from last night's OBS session. Did a live stream from the telescope. Hope you sort of like that. It's probably not the most interesting and exciting kind of live stream that can happen, but that's how it's going to be. When these two things, when this live stream and a obsession, overlap one another, I'm going to do them both at the same time, which means we're going to be outside. You're going to be looking at the screen, and I'm going to be collecting photons. So yeah, I'm probably actually going to lean more on the chat, to come up with things to talk about and stuff, because there's only so much I can say about there's a star and there's a galaxy and there's this and there's that. But last night's live stream was fun, and actually, collected data on one of my target stars. Got a little over 100 pictures there, which is pretty good. Then we moved over to Messier 77, which is a spiral galaxy, and got 100 pictures of those. And as soon as that was done, I sort of I think I ended the stream right before I finished that, and finished collecting those pictures. Got up, ran to the telescope, looked at the corrector plate at the front of the scope, and there was a thin layer of fog all the way around it, all the way, and it's like, oh, really? And I looked at my little device to show the relative humidity, and yeah, it was at 82%, which at that level and that temperature, things are going to do up really fast, and they did. So I looked at that. I also looked south of me, and clouds were starting to roll in, right? Kind of the neat thing about being at a dark site where I am is that the clouds are black, right? So I don't actually see lit up clouds. What I see are dark holes in the sky, right? Where there aren't any stars. And it's like, oh, so doing up on the telescope and clouds rolling in. As soon as I got the 100 pictures, it's like, okay, I'm done. And so I packed it all up, and haven't had a chance to look at that data yet. I've got to do what's called a data reduction, right? I've got to take all my calibration data, my flats and my darks, and use those to take the raw data and sort of reduce that to just what the data is, and not the raw data, which includes all the darks and all the biases and everything else in there. So still have to do all of that. That's just a moderately tedious process, but it's pretty easy, and I've got it down pretty well now. So it's just a matter of doing it, and I mean, it'll literally take me 15 minutes to do it. It's just tedious. So I have to make lists, and then I had just do all these things. I think at some point I'm actually doing that on a different computer, so I can't show it on this live stream. But maybe at some point I'll try to figure out how, because I guess it's sort of an interesting process, to actually take this raw data and convert it into scientifically valid data, where I can actually get some numbers out of it, some measurements of positions and measurements of brightnesses, and go from there, right? So yeah, that's just sort of going to be an ongoing thing. So that's the update with that. Pretty much I'm going to be doing this every clear night. I don't really care if there's a moon or not. The moon, brightens up the sky, but I don't really care much about that either. So yeah, I think that is just going to be an ongoing thing. And like I said, if this live stream and the OBS session overlap in time, I'll just do them both at the same time. I'll take the smartphone out, put it up on a tripod, like I do, and I'll just do a live stream from out there, and we'll have a good time doing that, I hope. And yeah, I think the only difference is that if I'm going to do that, I will definitely try to let everyone know, right? I'll make a short YouTube video, before sunset, or right around there, saying that I'm probably going to be observing. So expect the live stream to be outside. I'll post something over on the Discord server, and I'll probably tweet as well. So, and if anybody thinks I should do anything else, let me know. But I think that pretty much covers it. So here I'll check my weather too. Weather 606. Let's see what it says that it is here. I've had clouds all day. We actually had a little bit of rain too. There's Nightbot. Okay, so yeah, pretty warm. Relatively speaking, at least it's pretty warm. And I'm more humid than you are, Bobby. Look at that.
Yeah, the cha-cha too.
Yeah, what about that? I thought this was the desert. I keep thinking that. But then, of course, I realize what time of year it is, and here, this time of year, it is usually pretty wet. So our dry months start in February, March, and then I'll be dry until July. And then we got the monsoons for at least a few months. And then we have another dry spell, October, November, December-ish or so. So that's usually how that goes. It's advertised that this part of the world has about 300 clear nights per year, and it sort of depends on what you define as clear, but that's probably not too far off. That's probably a slight exaggeration. That's probably not even average. But for sure, more than half the nights of the year are clear. So 200 nights a year, yeah, are definitely clear. So yeah, I sort of hoping to be able to take advantage of all of those. I've got to have some projects to actually do, and so I'm thinking about those. And to that end, the current project I'm doing now is just trying to characterize my telescope system back there. See how good it actually is, right? Can I do very, very accurate measurements of positions of objects, and not only positions of stars, but positions of asteroids and comets, things that are moving too, right? And then can I also very, very accurately measure the brightnesses or the magnitudes of stars and galaxies and comets and asteroids and all those things? How accurate can I be? And looking at the data, I noticed this trend, which I wasn't quite sure why it was there. My first thought is that okay, the brightness that I'm measuring of these stars in my field of view are getting brighter because at that point, the moon was rising, and so the sky is getting brighter and brighter and brighter. And I'm sampling a little bit of the sky, so maybe that's what's going on. And right here live, wrote some code to actually do a linear fit to the brightnesses of 3 of those stars in my field of view versus time. And if it was the case that the sky was the cause of the brightening of these stars, then that brightening would be exactly the same for those 3 stars. And what we saw live here was that the brightening wasn't the same between all those stars. So it's like, okay, well, what is going on there? What's going on? And well, it turns out that what I thought wasn't going to be a thing actually is. And what that thing is called atmospheric extinction. Extinction is just a dimming effect that is a function of the altitude of your target object and a function of the color of your target object. So bluer objects will brighten a lot faster as they rise than a red object. And I didn't think that was going to well, I didn't think I was going to see that because I'm looking at these objects very, very broad band, right? I'm not looking at them through any kind of filter at all. I'm just, letting all the light come through, right? I'm not looking, just at the red wavelengths or just at the blue. I'm looking at everything, right? But if what I'm looking at is primarily blue, then the atmospheric extinction is going to play with the brightness of that. And like I said, you know, um, if the target, you know, like a star, is blue, then as it rises, right, as it gets higher in the sky, its brightness is actually going to change faster than a red star, pretty much in the same place. And that is precisely what I'm seeing. It's exactly what I'm seeing. I was looking at these 3 stars, and the faintest of those 3 is actually pretty red, and that had the smallest increase in brightness as it rose. So yeah. So now I'm going to have to take into account the extinction factor, and I'm going to have to you know, incorporate that to the analysis, and so that's sort of where I am there. I'm not quite finished with that. Sort of preliminary look actually looks pretty good. But yeah, I've got to take a pretty hard look at all that. And like I said, I've got to incorporate this this extinction factor, put it in my code. So yeah, that's sort of the next step. You know, today I sort of confirmed, you know, that extinction was the cause of that, and you know, taking out the extinction definitely, you know, flattens those curves out. So, you know, I'm not getting any kind of brightening anymore or anything. So that is really, really nice. So yeah, so that's
Scott,
so that's where that is.
What you need to do for science.
Do what I need to do for the science. Yes, yeah. It's you know, and you know, that's partially, you know, this reason for this live stream is to show you, you know, what the process is like. Now, I am definitely not an expert, but I'm also, you know, not a newbie at this either. So you know, I'm somewhere in between. You know, there are lots and lots and lots of people who are much better at this than I am, and there's lots and lots of people who are much worse at this than I am. So you know, I'm somewhere in the middle, but you know, I want to take you all along, you know, to show you what the process is, show you, you know, the obstacles and the stumbles and all of that, because that's part of, you know, the scientific process. It is work. It is hard, and that's why I say, you know, over and over and over again, you know, when we're looking at these scientific papers, right? It's an unbelievably huge amount of work, and thinking and analyzing, and you know, going over things over and over and over again, and you know, looking at the results of either, you know, processing of data or the output of models, and trying to understand what am I seeing, right? And when you see something strange, it's like, why is that happening, right? And in my case, what I'm doing here, and I mean, I'm not showing you all the details. I'm just showing you a few, you know, because the actual work is tedious and long, and you know, a lot of work, you know, takes place while I'm, you know, driving, or going to sleep, or waking up, or you know, watching TV or something. You know, I'm thinking about all these things. So that's where a lot of the work actually takes place. Is those times. And like I said, I'm definitely not extremely good at this. I'm definitely not extremely bad at this. So critical thinking is extremely important. Like I said, Space TV, howdy, by the way. Science, to me at least, has well, it stands on three legs, right? There's skepticism, and not cynicism, right? That's different. I'm talking about skepticism. That means, when you get something, it's like, what is this, right? I'm going to rip it apart. I'm going to try, you know, find something wrong with it, right? Um, uh, so that's leg one. Leg two is open-mindedness, right? You have to have as open a mind as you possibly can. You can't look at something and say, "Oh, come on," right? You can't close your mind off to things. You got to try. You've got to try to be as open-minded as you possibly can, right? You have to think outside of the box, right? We all of us, every single one of us, live in a box, right? Every single one of us do. Whether you know it or not, you do, right? And we can only see things inside of this box, right? We cannot see outside of this box. But there probably is things outside of this box, right? Probably. And that's where the open mind comes in, right? Is realizing that, okay, this is the box that I'm in, right? These are my biases. These are my experiences. This is my knowledge. All of that boxes us in, right? But to realize that there's probably something outside of that, right? That is the open mind. So you have to keep an open mind about things. So that's two. Number three, the third leg, is curiosity, right? That's the motivation, right? I mean, that is what motivates me for sure, right? I mean, I look at almost everything, and my reaction is, wow, that I'm in absolute awe of pretty much everything, right? And I want to know more about it, right? And so that is sort of the motivating thing. So curiosity, open-mindedness, skepticism, those are the three legs of science. And that's and then you've got the scientific process, right? Which is this, process fractal, where the output goes right back into the input, and it just feeds and feeds, just cycles and cycles and cycles. Was I taught critical thinking and skepticism at a young age? Or did I learn it myself? Space TV, I don't exactly know where I picked that up. I think a lot of that I did pick up more as an adult, right? Once I was sort of, out on my own, having to do things on my own, already sort of being, scientifically minded anyway. I think that was something that I probably did more or less learn on my own. Yeah, I think so. But yeah, I think it's pretty important for sure. For sure, if you're sort of boxed in, to thinking a certain way, and doing things a certain way, then you're going to sort of limit yourself in terms of what kind of results you can get. And I like my box to be, sort of as big as I can make it. And I I don't know if that's a good analogy or not. Probably not. But because I think we're all in boxes. We definitely are all in boxes. Maybe the size of the boxes are different, or the shapes are different, and that's not really a judgment call. That's just that's how it is. And I also don't mean to imply that everyone should get out of their boxes or expand their boxes and stuff. I don't think so. I think there's room for us all. So some people will, and some people can, and some people won't. And I think we need everyone. I think everyone is doing great just the way they are. And that's something that Fred Rogers taught me, right? So he I think he was a pretty strong influence on at least my thinking. That you're great just the way you are. And I think if we accepted um, people a little bit more that way, it might be a better world. Um, Instead of saying, well, you should do this or you should be like that. It's like, you know what? You're awesome. Just like you are. You be you. You don't have to be anybody else, right? In in Do you ever see that movie Forrest Gump, Bobby?
Oh yeah, I've seen that movie so many times.
Yeah. The uh, what was the girl's name? Jenny. She um, she asked him once. It's like, Forrest, what do you want to be? What do you want to be? And Forrest, he sort of backs up and he's like, I'm going to be me. And you know what? That's the right answer. That's exactly the right answer. You be you, and do it well, right? I mean, do it really, really well. And you know, that's precisely what I'm trying to do. Just be me, and actually, Joseph Campbell, right, said, follow your bliss, right? Find that thing, or find those things that just make you really, really happy, right? Give you a lot of joy, have a lot of fun, right? Have as much fun with things as you possibly can, and
Okay,
and
it's
and that's your
basically
groove.
asking, do you think more effort should be put into teaching skepticism at a younger age, and would it help make a better world?
Um, I don't. Yeah, like I said, I don't know if anything should necessarily be pushed pushed onto anybody, right? Maybe um, you know, we have so many examples throughout the history of the world of people who were skeptical, and we can sort of see the results of that skepticism. So, learning things like the history of science. I've got a book around here somewhere. Da, 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 da. I don't know where it is. Don't know where it is. It's a shoot. I'm looking on all my looking on all my bookshelves. It's a book about the great experiments in physics, and it goes through you know what the experiments were, and who the people were. I don't know where that book went. I need to find it. I've been rearranging things in here lately, so yeah, who knows? Who knows where I put it? I don't know, but I think looking at those giants and seeing what they did is might be a good place to start, at least. And making a better world, that's sort of a subjective thing. Yeah, I don't know what that means. Because if a better world means that everyone feels the same way and does the same thing and thinks the same way, I don't know. That sounds kind of boring to me. So yeah, we we've got this dichotomy, and it's the Buddhists they talk about balance, and so I sort of like that. So yeah, making a better world. I don't know. I don't exactly know what that is or means. Interesting to think about, though. Yeah, yeah, for sure. All right. Well, cheers. Hydrogen hydroxide tonight. I've got at least a couple moles here. So yeah, it's an incredibly huge number of molecules in this little jar here. Just absolutely amazing, the multitude that surrounds us. I mean, these bodies of ours are trillions and trillions and trillions of atoms, right? Much less all the living things, that are sort of making us go. I mean, where's the line between me and all these things inside that are sort of making it go? I don't know. Yeah, that's a hard one too. But cheers. Cheers to the universe. It's a pretty amazing place, and it's bewildering, and I hope it stays that way. All right, cool. I think let's do a quick object of the day. I think we should do a quick object of the day. And what we haven't done in a little while is an object of the day from the Messier catalog. So let's do that. And I do have Nightbot able to pick a Messier object for us, but let's go over to random.org and do it that way this time. Okay, Space TV is asking me more questions. What do I personally think is the most interesting mystery about the universe? I think the most interesting mystery about the universe is existence itself. That's what's called the hard question. Why is all of this here at all, right? Regardless of what's going on, right? Why is it that this is happening at all? Now, I'm pretty grateful that it is, but the possibility of this actually happening at all is extremely unlikely, right? Extremely. It's and that makes the entire universe bizarre, right? Completely bizarre. So so I think that's probably one of the most interesting thing is just the big question itself as to you know, why this, right? You know, what's the big deal here, right? I mean, why is it even here? Don't know. Don't know. Now, there are a lot of possible answers, right? Are they right? Are they wrong? I don't know. I don't know. Some people are pretty convinced of some of those answers, but I'm skeptical. I'm skeptical of most things. You know, infinity is a mathematical thing, um, and it's really, really, really easy to fall into, you know, these mathematical places. So a concept like infinity and a concept like zero, it doesn't. I don't think it really exists. Don't think it really exists. I think that's, you know, whatever those kinds of concepts are, I don't think we have a really good handle on those. Those are mathematical tricks that you know, solve certain problems for us. Um, but you know, the concept of nothing and the concept of everything um, seems to me to be, you know, two sides of the same coin. What that coin is, I don't know. I don't know. All right, let's do an object of the day, and I'm going to go over to random.org here. Let me set that up. Let me set that up really, really quick. You know, I was not planning on going too deep tonight, but I certainly enjoyed that from time to time. So, and of course, you know, these are my opinions. That's all it is. So, you know, um, take what I say very, very, very lightly, because what do I know? Well, I can answer that. Very, very little. So, uh, in fact, you know, you know, what do they say? I don't even know what I don't know. So, you know, how can I possibly think that I know anything at all? All right. Okay, there's random.org. But, you know, gives us a little bit of comfort and, you know, stability in at least thinking or believing that we know stuff. So, you know, whether we actually do or not, we probably don't. We're just making it up anyway. So, all right, I'm going to share my screen. Dun, 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 dun. Go to random.org. So there's 110 Messier objects. Charles Messier was a French astronomer back in the 1700s, and he was a comet finder. But you know, during his travels looking around for comets, he came across these other objects that well, he could either, you know, identify that, you know, were probably not comets, either because, you know, they look, well, you know, they didn't look like comets, or, you know, they were fuzzy things that didn't move. And he made a list of all these things, saying, you know, if you're looking for comets and come across, you know, a particular object, that doesn't seem to move or kind of looks funny, you know, he compiled a list and gave, you know, the coordinates, you know, the celestial coordinates in the sky, and said these are not comets. And you know, it was sort of a, you know, for him it was sort of a throwaway list, right? It's like, you know, these are junk objects, you know, junk somethings that I don't think he really cared that much about. But it turns out that, you know, these objects are bright galaxies and globular clusters and nebulae and they're quite interesting and quite exciting. And some of the brightest so-called non-stellar objects in the sky, things that aren't stars. Now, most of these things, I guess, with the exception of the nebulae, are actually made of stars, right? Stars comprise galaxies. Stars comprise clusters. But at that time, they really didn't have the technology or the know-how to figure that out. And we think that we've got a pretty good knowledge of that now. Could that knowledge change? Sure, why not? But there's 110 of them, so I've gone over to random.org, as you can see here, and I'm going to have it choose a number between 1 and 110, and then we'll investigate the Messier number associated with this. Except, I'm going to make a couple exceptions. If it's M42 or M31, I'm probably going to pick another one, because those are, not that they're boring, but those are, very, very well known, well studied. Even like M13, I might pass on. I reserve the right to choose a different one. So that's I've got all the power here. Wahaha! All right, here we go. Ready? Bam. So M20. All right, M20. I think we looked at that before. I don't remember. I think that's a globular cluster. Or is that M22? I don't remember now. I always try to guess or remember what the Messier objects are, because
it'd be better if you did keep a log of already seen objects.
I probably should, but yeah, that's too much work.
Why too much work?
I don't know. I have to keep track of things. That seems hard. I don't want to keep track of things. I keep track of too many other things. Maybe we should. Yeah. All right. Let's do it though. Let's go over to Simbad here. Simbad is a great jumping off point. It's a great astronomical database. Simbad has been around. I started using Simbad in 1991. And I've pretty much, I watched it evolve and grow, and it's a great resource, right? Because this is a database of all astronomical objects, right? Stars, galaxies, cluster, everything, right? So not just a catalog of galaxies, not just a catalog of stars. It's a catalog of everything. And what these folks do is they actually go, go into the literature and find this information and enter it to this database. So, once again, I'll say it again, just this huge effort, huge effort. And so, this is a pretty good jumping off point. So yeah, let's do it. M20. Doesn't look like I've searched for it. So, but yeah, M20. You know what? That's a cluster associated with the Trifid Nebula, right next to the Lagoon Nebula. So yeah, I think. Yeah. So see, and I think we have looked at this before, but let's look at it again. That because it's been, I don't know, months and months and months. I always thought that M20 was this nebula itself. And at least according to Sinbad, I guess I haven't investigated this enough, it's actually the cluster, the star cluster that is lighting up this nebula that is what they're designating as the Messier object itself. I think most people would say that the Trifid nebula is actually Messier 20, but either way, this is absolutely fantastic. Yeah, so this is a diffuse nebula and cluster of stars. And the nebula both emits light and reflects light. So we've got a little bit of both here, because the stars are actually inside of this nebula, and this nebula is this huge cloud of gas and dust that is, like I said, both glowing and also reflecting light. It's mostly hydrogen gas, but there's all kinds of other stuff too, right? I mean, pretty much every element is represented here. You can find magnesium and calcium and iron and oxygen and carbon, silicon, gold, silver, platinum. Wouldn't be surprised if there's plutonium and praseodymium and all of them, right? So, but yeah, all right, well, cool. M20 is an excellent choice. It's near the galactic center, right? And the reason I'm going to zoom in here a little bit so you all can see this.
Okay,
the reason why I say
he's got a good question. Is it possible for your fans to make a request for the object of the day?
Well, I'm gonna say no, because I really enjoy sort of the randomness, randomness aspect of that. So we really don't know what we're gonna get. Now, if you do have a special request, for a particular object, by all means, right? But I think I'm going to reserve object of the day, quote unquote, to this random process. But if you have anything interesting that think deserves to be looked at a little bit more, I'm totally open to that. Totally open. Yeah. And that can just be, a special object, special request object or something. We'll make up a name. We can make up names here. So, Space TV, I totally agree with you there. Cats, my observation about cats is that they are highly evolved, right? They have figured out, how best to live, and they do it, right? Yeah, that's all I have to say about that. So, LL Pegasi, okay. What I'm going to do is I'm going to copy and paste that over here. We'll do it right here. Let's see, Astro Live, and we'll call it, for lack of a better term, let's just call it object requests. All right, I put it on the list. Sounds like maybe a variable star of some sort, some kind of active object. So, yeah, all right, well, it's on the list. Yeah, I think that actually might be a little fun. So I think that's a good idea. for sure. All right, well, this guy is, like I said, very, very close to the center of the galaxy. And the reason why I know that is I can look at the galactic coordinates here, right? So the galactic coordinates have it at about 7 degrees east of the galactic center and less than 1/3 of a degree south of the galactic center. So very, very, very close to the galactic center. If you pull up, Stellarium or another planetarium program and look for M20, you'll see that it's really, really close to what we think is the center of the Milky Way galaxy, for sure. Now, in terms of celestial coordinates, here those are, right? So 18 hours, 2 minutes, 42 seconds, and a declination of -22 degrees, 58 minutes, 18 seconds. So, these are just two different coordinate systems. One is based on sort of the latitude and longitude of the Earth, projected right onto the sky. The galactic coordinates here are with respect to the galaxy, which is just, slightly different angles and distances and all of that. There are several different kinds of coordinate systems used in astronomy. It sort of depends on sort of what you're looking at the information for, right? Sometimes it's a little bit easier, to think in terms of galactic coordinates than it is, celestial. But it sort of depends on what you're after, right? So proper motion. So that's a measured value of how much motion these objects have in the sky as we see them. And these are in milli-arcseconds per year, so thousands of an arcsecond. So 1 arcsecond is 1/60th of an arc minute. And 1 arc minute is 1/60th of 1 degree. And of course, going all the way around, the celestial sphere is 360 degrees. So one arcsecond is 1/3600th of a degree. And they're talking here about 2 milli-arcseconds. So that's 2 1,000ths of an arcsecond, which, let's see, grab the handy dandy calculator here. 3,600, whoops, 3,600. Oh, yeah, so that's about, 1/1800th of a degree per year. It seems to be moving relative to us, right? So, of course, that object is moving, and so are we. So it's sort of a mutual thing, right? Radial velocity is how far away it's, or how fast it's moving either towards us or away from us. This negative value here says that it's moving slightly towards us, right? The distance is getting shorter and shorter and shorter. So yeah, 2.13 kilometers per second. That's pretty slow. So we and it are more or less moving sort of together, right? If you sort of combine the radial velocity with the proper motion here, all these numbers are really, really small. So relative to each other, we and it are sort of moving the same way. Not exactly, right? But yeah, those numbers are small. So relative to one another, we're not really moving all that much. So of course, a bunch of different names, usually just different catalogs. Yeah, lots of references. Most of the Messier objects are very, very well studied because they're big and they're bright, and we can see a lot of details. And so there are lots of things to see, right? I mean, in an object like this, right, where you have nebulosity, you have stars, you have just lots and lots and lots of things to actually see. It's naturally going to be well studied, especially because it's so bright, right? I mean, this object, did they give a magnitude here? Yeah, they're not really giving a visual magnitude, which is a little strange. Um, but the Trifid Nebula is probably a little too faint to see with the unaided eye. So you definitely, I mean, in a dark sky, you can definitely see this with binoculars. In a sort of a lit up sky, cityscape sky, you probably need a telescope to see much of anything at all. And of course, and I'm going to try to say this as much as I possibly can. Um, when you look at this object through a telescope, right, it is not going to look like that. It just absolutely 100% does not look like that at all. What you'll see is, a bunch of stars and maybe some fuzz around them. Maybe a little bit of structure, some dark areas and some light areas and all that, but you're not going to see, all this detail and color and everything. You're just not going to see it at all. Our eyes just don't work that way. Now, all that color is there, right? It's all there. It's all extremely real. Our eyes just aren't sensitive to those kinds of things. But if you stick a camera on your scope and take a long exposure, you will start to see something like this. The reason why it's called the Trifid is kind of hard to see here, but there are these dark areas. Maybe I can find a better shot of that, just so you can see why it's sort of called the Trifid Nebula. Yeah, let's just go to images here. There's probably trillions of images. Yeah, let me grab a big one. Let's grab the biggest one we can. I don't know. What's our favorite here? This one? Sure. This is astronomy picture of the day. That's quite appropriate. So the reason why it's called the Trifid is because these dark lanes here sort of divide this nebulosity up into three sections. The tri, right? Trifid. It's it's sort of a stretch of the imagination, but that's what you have to do in astronomy a little bit. You have to use your imagination a little bit, and but obviously, a beautiful cluster. This red part is the emission part, right? So this is gas and dust that's glowing. This blue part here is actually the reflection part. So this gas and dust is actually reflecting light from stars, probably the same stars in here. So we have emission, much like a neon bulb, right? The same kind of idea, and a reflection. So looking at like a gas and dust cloud, reflecting light. Same kind of thing. And you also have all these dark features in here too, and some great structures. It's a beautiful thing. Now, like I said, you are not going to see this when you look through a telescope. Absolutely not. You'll see a little bit of fuzz here. Maybe you'll see some of these dark lines here. You're not going to see any of this. You're not going to see any of this out here at all. But like I said, you stick a camera on there and take a long exposure. And if you're good at it, you got to be good at this. You'll get a picture like this. And of course, it's absolutely gorgeous, right? It's absolutely fantastic. And these diffraction spikes are not actually part of the stars. They're part of the telescope itself. So but these can be added with software, or they're just sort of naturally there, as part of the optic system. And for the PR purposes and stuff, it sort of makes it pop a little bit more. I mean, I totally understand that. So it's beautiful, right? I mean, it's absolutely fantastic. There isn't a lot of scientific value here, but that's only part of the value, right? There is definitely just sitting back and appreciating this and going, wow, this thing is in the same universe as I am. And that's pretty incredible. But it is nice, to see, the colors of the stars here. You can see that there's reds and oranges and whites and blues, and, so that's a pretty good shot, really, really nice shot. Anyway, so there's the Trifid. This image was taken with the Digital Sky Survey. Now, I don't think that the Sloan Digital Sky Survey took images of this part of the sky, but let's take a look anyway. Let's see if we get anything. No, we don't. But what we can do is we can go over to Aladdin Light here and look at different surveys. Now, I'm not quite sure what all of these are. Let's see if I can pick out a few. 2MASS, I think, is an infrared survey. So you can see that, oh, I'm zooming out here, sorry, turn black. Come on, you can do it. So, well, come on. If you look at the same region of the sky in the, I guess, is 2MASS an infrared? I don't remember. But a lot of the nebulosity goes away. Look at that. Or at least it's different, right? Spitzer, I think, is infrared. Let's see if Spitzer looked at it. Yeah, it did. So that's one of the cool things in astronomy, is that we can look at the same object at different wavelengths, and every single time it sort of looks new, right? And that's nice. IRIS was also an infrared telescope. Did it look in there? IRIS may not have looked there because it's so close to the galactic center that it was probably just blown out. I don't know what a lot of these other ones are. What is that? Finkbeiner. So this is a hydrogen alpha survey. Let's see. Okay. Low resolution. So we're just getting a blob. Mellinger color optical survey. Oh, okay. Again, kind of low resolution, right? But we're seeing the same thing, right? Here's the emission, the red part, and here's the reflection, the blue part. Slightly rotated and all that, but it's easy enough to translate in our brains. Gamma rays. Again, pretty low resolution. But again, you know, I mean, it looks different. This looks like the galactic disk, actually. So pretty cool, pretty cool. Glimpse 360. So this is in the infrared, it looks like. Pretty cool. What is 2-mass? JH and K. So yeah, that is definitely in the near infrared, just outside of the optical range. Spitzer, Allwise. Let's look at Allwise. Did Allwise look at it? Oh, it did. Just an unbelievable number of stars in here, though. Just incredible. Absolutely mind-blowing. All right, well, cool. You know, the Trifid is as I said, you know, a very, very well-studied object. So probably what we should do, let's look at the distances, and I guess there's a proper motion measurement here too, and then maybe reserve some of tomorrow to look at least some of the references, maybe some new ones, maybe some old ones. I like to go back and look at the oldest records, right, and see, you know, what they were thinking about this object, you know, 100 years ago, which we can now do. So, all right, well, at least according to this, when they...
You, Brock. Welcome.
Who's over there?
Earth Radio.
Oh, hey, ERT. Nice to see you. I sent you an email. I don't, let me know if Friday is good, because I can't make any plans unless you're able to confirm. So, but Friday morning sounds good to me. So, okay, well, back in 2005, it looks like they made a distance measurement here. So 816 parsecs, that's what the PC is. And a parsec is 3.26 light years. So I like to convert that to light years because that sort of, I don't know, makes it easier for me to get an idea about how far away it is, right? So 2,660 light years away. So that's kind of an interesting thing about this, right? It's located, at least from our line of sight, near the galactic center, but the galactic center itself is something like 30,000 light years away, right? So this nebula just so happens to be, you know, right in the line of sight of the center of the galaxy, but it's not even close to the center of the galaxy. In fact, it's closer to us than it is to the center of the galaxy. It just so happens to line up with it, right? So that's kind of interesting. Yeah, it's only 2,600 light years away. That's practically next door, almost. I mean, yeah, that's pretty far. But yeah, you know, don't let these big numbers, you know, confuse you too much or overwhelm you too much. That, you know, it. I think a lot of astronomers like to throw out all kinds of big numbers and you know, be really, you know, dramatic about stuff. And what I've observed, at least, is that the universe is fractal, right? And that is, you know, we basically see exactly the same thing at any scale, right? At any scale, there are incredibly amazing things. So, you know, just because it's a big number, that's no big deal, right? Distance is really, really important, though. if we want to sort of know or infer anything sort of fundamental about the objects we're observing. Because if we know how far away they are, then we can sort of use the observations that we have to infer things like what's it made of, um, um, what are the motions like, how bright is it really, what kind of processes are going inside, um, all of that. So distance is important, but don't get too hung up on the numbers, right? Because it's just a number, and numbers are pretty arbitrary. Like I said, lots of astronomers throw these numbers out, and we're all supposed to be really, really impressed by that. It's like, wow, the Andromeda galaxy is 2.2 million light years away, and 1 light year is 6 trillion miles, and on and on and on and on and on. It's like, chill out a little bit, look up, enjoy, right? Enjoy it for what it is, and don't worry too much about all these big numbers and 400 billion stars and all that. It's like, yeah, there's a lot of stars there, and I think it's amazing, right? But don't get stuck on the numbers, because that's really, really easy to do. Really, really easy to do. So look past that, look at the information you have, and what I do, right, is I'm in awe. I'm in absolute awe. I mean, I'm just in wow all the time. So, all right, well, with that, one more of these. Cheers. And I'm going to get out of here for today. Now, it sort of looks like the next few nights, next couple of nights are going to be cloudy here. So that means I will be right here instead of outside. But if it is clear, like I said, I'll try to let you know beforehand, so you can sort of coordinate that and decide if you want to come in or not. But yeah, I think that's it for now. We'll continue looking at Messier 20 tomorrow for a little bit. We'll look at a few of the papers. Like I said, let's look at some of the latest stuff and some of the really, really early stuff, and that'll sort of bookend that really, really well. But yeah, it's a very, very, very hugely studied object. Lots and lots and lots of info there. Tons. I mean, lifetimes, right? Multiple lifetimes worth. Just spending reading all that stuff. Much less, collecting the data, doing the analysis, doing the work, writing the papers. All of that. It's just an almost an unfathomable amount of time and effort and work goes into that stuff. And you got to admire the people who will do that. It's pretty crazy, right? I mean, it takes a crazy person to do that, and that's what astronomers most definitely are pretty crazy. I think the universe has just completely driven us into total madness, and extremely obsessive, where it's like we want to know, we want to understand, and it's so cool. All of it is so incredibly cool. So all right, and that's why I'm doing this, because it's fun and it's awesome. All right, well, I'm going to get out of here for now, so take care. Have a great evening, a great day. Make sure to subscribe if you haven't. Hit the bell, ring-a-ding-a-ding. thumbs up if you so desire. Make some comments. Spread the word. Spread the word. I'm trying to spread this passion around, right? I'm not trying to teach. I'm not trying to communicate. I'm not trying to, cast this wide net to try to, pull people in. No, I'm here to spread the passion, right? I'm trying to push dominoes down, right? That's what I'm trying to do. And that's it. All right. So take care, everybody. I will see you in about 22 hours and 34 minutes. Take care. Peace, cheers, and all that. And I will see you later. Bye.